Dear students of second MSc Chemistry, in the previous class we saw what is meant by chemical shift. So chemical shift is a derived unit for the frequency of absorption in NMR spectroscopy. It is indicated by the symbol delta. It is given by the expression nu sample minus nu TMS divided by oscillator frequency into 10 to the power 6. Since it is multiplied by 10 to the power 6, the unit for chemical shift value is parts per million. And we saw the reasons for using the reference compound, namely tetramethylsilane. Tetramethylsilane is the reference compound. We saw the reasons already. Now, we made a comparison between the 60 MHz instrument and a 100 MHz instrument. In a 60 MHz instrument, if the chemical shift value delta is 1 parts per million, it refers to 60 Hertz. Whereas in a 100 MHz instrument, if the chemical shift value delta is 1 parts per million, then it refers to 100 Hertz. That is the difference. So based on this, we saw how a 60 MHz instrument, 100 MHz instruments are working in NMR spectroscopy. And after that, we moved to the factors which are influencing the chemical shift values. We saw how shielding and deshielding due to electronegativity of the substituent affects the chemical shift value. We have seen many examples. Tetramethylsilane, it is electropositive, that is the reference compound. So the chemical shift value for that compound is assumed as 0. And we have the substituted compounds. Among the halogens, if you compare, the electronegativity of the halogen increases from iodine to fluorine or decreases from fluorine to iodine. So as the electronegativity increases, the chemical shift value also increases from iodine to fluorine. It is such a comparison is given in William Kemp. I told you the reason also. Because of the increase in electronegativity, the electrons involved in the chemical bonding, which are shielding the nuclei of a proton, are pulled by the substituent. So the protons are experiencing a greater deshielding effect. They are experiencing a higher magnetic field. As a result, the chemical shift values are higher. This we saw in the last class itself. And we saw how electropositivity of the substituents are affecting, and we saw what is meant by van der Waals deshielding. It is the operation of effect through space. So that is observed in stereochemically complicated molecules. And after this, we shall be moved to the anisotropic effects. Already in the last class itself, I have told you what is meant by anisotropy. It is a term derived from crystallography. So, isotropy means uniformity. The opposite word is anisotropy. The crystalline compounds are anisotropic in nature. They don't have a uniform arrangement. The arrangement depends on the direction. So, for example, in sodium chloride, we have sodium atoms, after that chlorine atoms, and after that we have sodium atoms. It is the ionic compound. So, depending on the direction, the arrangement of atoms vary. The physical properties that are observed with the crystalline compounds also varies, and they depend on the direction. This is called as anisotropy. So, anisotropy means a difference. There is no uniformity in the molecule. Just like that, if you place an organic molecule over a magnetic field containing a carbon-carbon double bond, a carbon-carbon triple bond, or a aromatic ring, benzene, or a carbonyl group which has a carbon-oxygen double bond, there you have a pi bond. So the circulation of pi electrons in the molecule, when it is placed over a magnetic field, produces a secondary magnetic field. The secondary magnetic field is not uniform around the molecule. In some cases, the secondary magnetic field is aligning with the applied magnetic field, and in some cases it is opposing the applied magnetic field. So if you have a proton in such molecules which are showing the anisotropic effects, then the chemical shift values differ. The chemical shift values are varying or they are affected by the position of the protons. If the protons are lying in the deshielded area, they will experience a higher chemical shift. The chemical shift value will be higher. In some cases, the protons are lying in a shielded area, so they are experiencing a lesser magnetic field and the chemical shift values are also lower. I have given various structures. See, the carbonyl compound. The chemical shift value is in the range say 9.5 to 10. You have ethylene, the chemical shift value is in the range say 4 to 8. And for benzene it is 6 to 9, and for ethylene, acetylene it is 1.5 to 3.5. We saw the reasons one by one. First we saw the circulation of pi electrons in alkenes or compounds containing carbon-carbon double bond. This is the secondary magnetic field that is produced by the circulation of pi electrons when a molecule of ethylene is placed over a magnetic field. We saw how anisotropic effect is operating in the last class itself. So the protons of ethylene are highly deshielded. The protons of ethylene or any carbon-carbon double bond lie in a region where the magnetic field is aligning with the secondary magnetic field produced by the circulation of pi electron is aligning with the applied magnetic field. So the protons are experiencing a higher magnetic field, the chemical shift values are higher. This we saw in the last class, and for these we represented it with the help of a geometrical diagram where the axis is passing through the center point. Already we have discussed, even then I am repeating. So if I discuss the matter repeatedly, you can easily understand the subject. So through the center point we have an axis that is passing through. If you draw two cross lines at an angle of 36 degree with respect to the center point, then you will get two cone shaped structures. So if the proton lies in the cone shaped structures, then it experiences a deshielding effect. It experiences a higher magnetic field. The chemical shift value will be higher. In a molecule of ethylene, the protons attached to the carbon-carbon double bond are lying in the cone-shaped structures only. So they experience a higher magnetic field. The chemical shift values are higher. This we saw in the last class, and we have one example. See, in a molecule of alpha-pinene, we have three methyl groups. The methyl group attached to the carbon-carbon double bond, and you have a gem dimethyl group which is far away from the carbon-carbon double bond. But the two methyl groups, they are identical in their chemical environment. So they should show same chemical shift value, but one methyl group delta value is 0.73 and another one methyl group delta value is 1.27. So there is a difference in the chemical shift value. The reason is that one of the methyl group lies in the deshielded area caused by the circulation of pi electrons when a carbon-carbon double bonded compound like alpha-pinene is placed over a magnetic field. So this is the reason for the difference in the chemical shift values of the gem dimethyl group that is attached that is observed in alpha-pinene. This example we saw in the last class. And after this, we moved to the carbonyl group. So let us see how the carbonyl compounds are showing an absorption. See, the carbon-oxygen double bond, it also has a pi bond. So because of the circulation of the pi bond, you produce a secondary magnetic field. Just like the molecule of ethylene, the anisotropic effect shown by the carbonyl group is also shown by this geometrical diagram. In this geometrical diagram, you should be very careful to construct this geometrical diagram to understand the anisotropic deshielding effect that is operating in a carbonyl compound, for example in an aldehyde, namely benzaldehyde or acetaldehyde, whatever it may be, formaldehyde. You should imagine the axis that is passing through the center point of oxygen atom. So it is not through the center point of the carbonyl group, it is through the center point of the oxygen atom. Imagine an axis. With respect to that axis, if you draw two cross lines at an angle of 43 degree, then you get two cone-shaped structures. These are all geometrically designed. So from theoretical calculations, they have designed these geometrical structures to prove the anisotropic effect that is operating in the carbonyl group. We need not bother about the theoretical calculations, that is beyond our discussion. So let us leave it with the geometrical structures only. So with reference to the central axis, if you draw two lines at an angle of 43 degree passing through the center point of the carbonyl oxygen, then you get two cone-shaped structures. So in the cone-shaped structures, if the proton lies in these cone-shaped structure, they are experiencing a deshielding effect due to the circulation of pi electrons between a carbon-oxygen double bond. Here in the molecule of aldehydes, we have the proton that is lying in the deshielded area only. So the chemical shift value for the carbonyl group is higher in formaldehyde or whatever may be formaldehyde, acetaldehyde or benzaldehyde. Next, let us see the anisotropic effect that is operating in a molecule of acetylene or any compound containing carbon-carbon triple bond, alkynes. Alkynes are supposed to contain carbon-carbon triple bond. The deshielding effect or anisotropic effect produced by the alkynes is discussed in page number 102 in organic spectroscopy by William Kemp. Please go to page number 102 and in organic spectroscopy by William Kemp or any spectroscopic book that is available with you. You can refer P.S. Kelsey, organic spectroscopy by applications of organic spectroscopy by P.S. Kelsey. You can refer organic spectroscopy by we have another one Indian author. I forgot the name. It doesn't come to my mind immediately. Later on it will come. I will tell you. So the anisotropic deshielding effect, shielding effect is also shown by the alkynes. Let us see how the alkynes are showing the anisotropic deshielding and shielding effect. So this is the circulation of pi electrons in I want to show the whole picture. See, you have two pi bonds between the carbon-carbon atoms in a molecule of acetylene. See, a pi bond is formed between two p orbitals because of their overlap in a sidewise manner. Actually, these pi orbitals are perpendicular to the plane of the carbon-carbon sigma bond. In a molecule of ethylene, we have two planes. In one plane, the molecule is remaining. In another plane, the pi electrons are circulating. If you move further to a molecule of acetylene, here we have two sets of p orbitals which are mutually perpendicular and they are perpendicular to the plane containing the remaining molecule also. So, the pi electron is circulating like a pipe-like structure. It is cylindrical in shape. So, the circulation of pi electrons around a carbon-carbon sigma bond is in the form of a cylindrical shape. So, because of the circulation of pi electrons in a carbon-carbon triple bond, secondary magnetic field is produced. I have shown the direction and the arrow marks are indicating the direction in which the applied magnetic field is aligning with the secondary magnetic field produced by the circulation of pi electrons in a molecule of acetylene. So from the structure it is very clear that in some places it is offering paramagnetic effect. Which one? The circulation of pi electrons offers a paramagnetic effect and in some cases it is offering a diamagnetic effect. So B0 is your applied magnetic field. The field is applied from the bottom side. So the circulation of pi electron is also shown. It is in the form of a cylindrical shape. So just like a cylinder, the pi electrons are circulating, so the secondary magnetic field is produced. See, from the diagram it is very clear that the protons of acetylene are lying in an area where the secondary magnetic field is opposing the applied magnetic field. So as a result, the protons of acetylene are experiencing a lesser magnetic field. They are shielded, they are experiencing a lesser magnetic field. So the chemical shift values for the protons of acetylene is lower than a carbon-carbon double bond or a carbon-oxygen, proton attached to a carbon-oxygen double bonded compound, aldehydes, formaldehydes, acetaldehydes or benzaldehydes. So this is the reason. That is, the protons of acetylene lie in an area where the secondary magnetic field is opposing the applied magnetic field. So because of this, the protons, even though acetylene molecule has two carbon-carbon double bonds, two carbon-carbon pi bonds, the secondary magnetic field is produced powerfully or is produced with enough strength, but the protons unfortunately are lying in an area where the secondary magnetic field is opposed by the applied magnetic field. So the protons are experiencing a lesser magnetic field when compared to the protons of ethylene or any carbonyl compound aldehyde. So the chemical shift value is lower. Now let us move to the next example. See, here we are discussing about the circulation of pi electrons in an aromatic compounds, I already told you, aromatic compounds are having a pi system which is conjugated. Benzene molecule has 3 carbon-carbon double bonds. The 3 carbon-carbon double bonds are conjugated with each other. They are delocalized. So the pi cloud is delocalized over all the 6 carbon atoms in a molecule of benzene. Just like benzene, we have naphthalene, anthracene. These are all some of the polycyclic systems. So naphthalene, anthracene, they are polycyclic system in which the benzene rings are fused in a linear fashion. And we have another type of molecule, phenanthracene, acinaptacene. They are angular series where the benzene ring is fused in an angular manner. So after naphthalene, anthracene, the benzene ring can be fused with naphthalene or anthracene in an angular series. So that gives you a series of molecules, namely phenanthracene, acinaptacene. So you get 2 types of benzene molecules. You have 2 types of aromatic molecules, and you have 3rd type of aromatic molecules also. Later on we will see an example. That is pyrene, where 2 or more benzene rings are fused with each other. One benzene ring is fused with 2 or more benzene rings. Such a system is called as a perifused aromatic system. So, among the aromatic compounds, we have 3 types of aromatic compounds. One is linear fused aromatic compounds like naphthalene, anthracene. Angular fused aromatic compounds, that is phenanthracene and acinaptacene. And you have polyfused aromatic compounds like pyrene. We are going to see the aromatic character that is shown by pyrene also. So, in all these cases of aromatic compounds, the circulation of pi electrons in the aromatic molecule is above and below the plane of the molecule. So, since the pi cloud is circulating above and below the plane of the aromatic molecules are planar. That is one of the important characteristics. All the aromatic molecules are planar in structure. So, these pi electrons are circulating above and below the plane of above and below the plane containing the aromatic molecules. So as a result, secondary magnetic field is produced in the aromatic system. So the anisotropic shielding and deshielding is also offered by the aromatic compounds. See, this is the anisotropic shielding and deshielding effect associated with the circulation of pi electrons in an aromatic molecule like benzene. Look at the protons. See, the protons are very close to the arrow mark, where the applied magnetic field is aligning with the secondary magnetic field that is produced. So the circulation of pi electron is indicated. Benzene molecule is planar. Above and below the plate we have the pi cloud which is circulating. Now when it is placed over a magnetic field B0, you can see the secondary magnetic field with the help of the dotted lines. So in some places the secondary magnetic field is aligning with the applied magnetic field B0. A paramagnetic field is produced. The protons are experiencing a higher magnetic field. So the chemical shift value is higher for the protons of benzene. There are some locations where the secondary magnetic field that is produced due to the circulation of pi electrons is opposing the applied magnetic field. In such cases, suppose if you have a proton, the protons will experience a lesser chemical shift due to the shielding anisotropic offered by the circulation of pi electrons. So the protons of aromatic compounds and substituted aromatic compounds, if they lie in the deshielded area, they will show a higher chemical shift value, whereas if they lie in a deshielded area, the chemical shift value will be lower. So this is, we have some examples also. Let us see the examples one by one. See, look at the molecule. This is 1,3,5-hexatriene. Organic molecule 1,3,5-hexatriene. A methyl group is attached to carbon number 4. Heptatriene, 7 carbons are there. 1, 2, 3, 4, 5, 6, 7. 7 carbons are there. So this is a 1,3,5-hectatriene. Hexa, hepta, octa, nana. Octa means 8, nana means 9. So hepta, 7 carbons are there. 7 carbon skeleton. So this is your heptatriene. Actually, there is a mistake in this structure. One of the carbon-carbon double bond is not conjugated. The other two are conjugated. So you can redraw the structure. In the next class itself, I will correct it and I will explain once again. Now you look at, you can draw the structure of 1,3,5-hexatriene or a heptatriene like this. See, we have 3 carbon-carbon double bonds in 1,3,5 heptatriene. So a methyl group attached to one of the carbon-carbon double bond, it shows a chemical shift value delta of 1.95. If you compare the chemical shift value of the methyl group that is attached to a polyolefin like this with that of aromatic compounds. See, what is the name of this compound? C6H5CH3. Methyl group is attached to, or methyl group is substituting a proton in benzene. So this is your toluene. We all know. Simple compound toluene. If you record the NMR spectrum for this molecule, then the protons of methyl group show a chemical shift value delta value is 2.34. So you compare the chemical shift values of a methyl group that is attached to a polyolefinic system like this. The delta value is 1.95, whereas the methyl group of toluene shows a chemical shift value, it is around delta value 2.34 parts per million. The value of the methyl protons chemical shift value is found to be higher than the previous compound. So toluene shows a higher chemical shift value. What is the reason? The reason is very simple. The protons of methyl group lies in the area where the secondary magnetic field produced by the circulation of pi electrons in benzene is aligning with the applied magnetic field. So, the protons of methyl group in toluene, they experience a anisotropic deshielding effect. They are not experiencing a anisotropic shielding effect. Because of the anisotropic deshielding effect that is experienced by the protons of toluene, methyl protons of toluene, see, the chemical shift value is very close to delta value 2.34. So, this is the observation that is made experimentally. Let us see a few more examples. See, this is a compound called as 18-Anisotropic. If you study about aromaticity, you have studied about aromaticity in the first MSc class itself. So, anulines are conjugated double bonded system. Because of their conjugation and delocalization, anulines also show aromatic character, just like our molecule of benzene. So, just like benzene, they don't have 3 carbon-carbon double bonds, or naphthalene 5 carbon-carbon double bonds, which is conjugated in a polycyclic system. So, whereas anulines are macrocyclic systems where the carbon-carbon double bonds are conjugated. The carbon-carbon double bonds can be delocalized. They satisfy the condition for aromatic nature. They obey the 4n+2 rules also. So, because of these two valid points, the aniline compounds are showing aromatic character. And the aromatic character shown by anulines is also confirmed by spectroscopy. See, here you have 18 carbons. This is an aniline system. You can draw this structure. You can have a practice of, you have to practice. If you simply look at the structure and go to the examination hall, it will be very difficult for you to reproduce the structure. So, have a practice. Draw the structure of 18-Aniline with the help of a paper and pen or pencil. So, 18-Aniline is a conjugated system. It has 3 plus 2, 5, 5 plus 4, 9. 9 carbon-carbon double bonds. Each carbon-carbon double bond is made by 2 pi electrons. So, 9 into 2, 18 pi electrons. 18-Aniline is a planar molecule. 18 within the square bracket, I give the number. That means it is a aniline system containing 18 carbons. All these things we have studied in aromaticity itself. If you don't remember, then go to your notes or material that is given to you for the aromaticity chapter. You can find 18-Aniline. 9 carbon-carbon double bonds are there. So, 9 into 2, 18 pi electrons. They satisfy the 4n+2 rules also. 4n+2, if you put n is equal to 4, then 4 into 4, 16, 16 plus 2, 18 electrons. So, 18-Aniline is shown is obeying all the rules for aromaticity. It is a planar molecule. It satisfies the Hund's rule of maximum multiplicity. It has conjugated pi system. So, because of this, 18-Aniline was considered as a aromatic molecule since it satisfied the 3 rules for the aromatic nature. But it has to be proved spectroscopically also, another evidence. If you record the NMR spectrum for 18-Aniline, then 18-Aniline has 6 inner protons and 12 outer protons. So, the 12 outer protons are showing a higher chemical shift value. Delta value is 8.9. Whereas the inner protons, they show a chemical shift value which is lower than the reference compound itself, tetramethylserine. That is why it is indicated with a minus symbol, minus 1.8 parts per million. Actually, the chemical shift values are calculated. It is a derived unit with reference to the tetramethylserine. We assume that the compound tetramethylserine shows a chemical shift value which is assumed as 0. So, 18-Aniline has 6 protons whose chemical shift values are lower than delta lower than the reference compound, namely tetramethylsilane. The delta value is minus 1.8. And we have 12 outer protons. The 12 outer protons are showing a higher chemical shift value. The delta value is around 8.9. So this itself is a proof that the pi system that is circulating in 18-annuline produces anisotropic shielding and deshielding effect. The 18 protons of annuline lies in an area where shielding and deshielding effects are produced by the circulation of pi electrons. Out of the 18 protons, the 6 protons are lying in an area where there is greater shielding effect offered by the circulation of pi electrons with respect to the external magnetic field B0 that is applied. So the chemical shift value is lower than tetramethylsilane itself. Whereas we have 12 outer protons, the protons which are in the periphery of the 18-annuline molecule, they are experiencing a higher magnetic field. The chemical shift value is higher. The reason is the secondary magnetic field in those areas produces a paramagnetic effect. The secondary magnetic field is aligning with the applied magnetic field. So the protons, 12 outer protons are experiencing a higher magnetic field. Definitely there will be a question. If you sit for any Viva or C, or if you sit for any interview in a private company, then people will ask you, if you are interested in nuclear magnetic resonance spectroscopy, that is PMR spectroscopy, any examiner or any person who is interviewing you will ask a question from 18-annuline. What about the chemical shift values of 18-annuline? The 12 protons are showing a higher chemical shift value when compared to the 6 inner protons. The 6 inner protons are showing a lower chemical shift value. That too, it is a negative value, minus 1.8. What is the reason? So you should explain the difference in the chemical shift values for the protons of 18-annuline based on the anisotropic shielding and deshielding effect that is produced due to the circulation of pi electrons. And you can extend your discussion further by proving that 18-annuline is an aromatic molecule because it is obeying all the conditions for aromatic nature, and it is proved spectroscopically also. The protons of aromatic system, they differ in their chemical shift value, and it is also shown by the 18-annuline system, which shows anisotropic shielding and deshielding effect. So that itself is a clear evidence that pi electrons are circulated and they are satisfying the Huckel's rule, and 18-annuline is an aromatic compound. Let us move to the next example. See, as I already told you. So this is your perifused system. I will show you pyrene. If you are interested, you can refer the perfused ring system. Just like pyrene, we have plenty of molecules. If I discuss all those things, that itself will become a lecture. So I limit with pyrene alone. So in pyrene molecule, we have 4 benzene rings which are fused. Here, you may have a confusion. See, pyrene molecule, when it is methylated, then you have dihydrodimethylpyrene. Dihydrodimethylpyrene. By a chemical reaction we can methylate or we can synthesize dihydrodimethylpyrene. So in dihydrodimethylpyrene you have 8 carbon-carbon double bonds. See, 3, 2, 7. 7 carbon-carbon double bonds are there in dimethylpyrene, dihydrodimethylpyrene. 7 carbon-carbon double bonds means 7 into 2, 14 pi electrons are there. Dihydrodimethylpyrene, it is a system like our, the system of our dimethylpyrene is just like our 18-annuline. So we have 7 pi systems, 7 pi bonds, 7 into 2, 14 pi electrons. If you apply the Huckel's rule, 4n plus 2 rule, n is equal to 3 becomes 4 into 3, 14 pi electrons. Huckel's rule is satisfied. And the pi system is conjugated. So as a result, the dihydrodimethylpyrene is an aromatic compound. It is confirmed. The aromaticity of dihydrodimethylpyrene is confirmed. But it will be misleading. If you look at the structure of pyrene, then pyrene has one more carbon-carbon double bond. So it has 8 pi bonds, 8 into 2, 16 pi electrons. If you apply the 4n plus 2 rule, pyrene will not obey the 4n plus 2 rule. If you put n is equal to 3, 14 pi electrons are there. If you put n is equal to 4, then 18 pi electrons are there. So to satisfy the Huckel's rule, either you should have 3 pi bonds, the n value should be 3 or 4. But here in pyrene, if you calculate the total number of pi electrons, then the value comes around 16. It will not be 18 or 14. The value is 16. Even then, pyrene shows aromatic character. The explanation is given. Suppose if you consider the central carbon-carbon double bond, I failed to draw. See the dimethyl group. How the dimethyl group is produced. Originally in pyrene, you have a carbon-carbon double bond that is saturated by methylation. So you have dihydrodimethylpyrene. Whereas in pure pyrene, unsubstituted pyrene, you have a carbon-carbon double bond. So each system is the carbon-carbon double bond, third carbon-carbon double bond is shared by the 4 rings. In such cases, we have the aromatic character. Though pyrene is not satisfying, the 4n plus 2 rule in total, if you consider each and every ring, it is satisfying the 4n plus 2 rule. So, it is a trivial situation, just like our wave particle dualism in quantum mechanics. So, pyrene molecule, we have several examples like this, and we can do lot of research work. We will come across lot of research papers based on these pyrene and acene, another molecule, which has some 8 fused ring system. So it is a more complicated system that the discussion will go on. So pyrene is also an aromatic compound. If you consider each one as a separate benzene molecule, if it is methylated, you get dihydrodimethylpyrene. That is also an aromatic compound. See, the methyl protons of dihydrodimethylpyrene, they show a chemical shift value. The chemical shift value is much lower than tetramethylserine. It is much lower. It is much upfield of tetramethylserine. So, the delta value is minus 4.2 parts per billion for the methyl protons. So, in the examination, if you sit in any viva voce, people will ask you. If you compare the chemical shift values for the protons of pyrene and dihydrodimethylpyrene. In dihydrodimethylpyrene, you have 2 methyl groups. The 2 methyl groups are showing a chemical shift value in negative, in minus, they are showing a minus value, that is down than tetramethylserine, minus 4.2 parts per million. What is the reason? The reason is dihydrodimethylpyrene has 7 pi system which are pi bonds which are conjugated. The circulation of the 7 pi bonds, just like our 18 aniline, produces a secondary magnetic field. Unfortunately, the protons of the 2 methyl groups in dihydrodimethylpyrene lie in an area where they are experiencing a greater shielding effect produced by the circulation of pi system in dihydrodimethylpyrene when it is placed over a external magnetic field B0. So this is the reason. So because of the anisotropic shielding and deshielding, the protons of 18 aniline and dihydrodimethylpyrene, they show a difference in the chemical shift value. The methyl protons of pyrene shows a negative chemical shift value minus 4.2 parts per million because the protons lie in a shielded area produced by the circulation of pi electrons in pyrene, dihydrodimethyl pyrene. Similarly, in 18-aniline also, the 6 inner protons are showing a negative value. It is minus 1.6 parts per million, and the reason is the 6 inner protons are lying in an area where the circulation of the pi electrons in 18-aniline produces a secondary magnetic field, and the secondary magnetic field is opposing the applied magnetic field, so that 6 protons are showing a negative chemical shift value in 18-aniline. So let us see a few more examples also. See, just like the anisotropic shielding and deshielding effect offered by the circulation of pi electrons, the anisotropic shielding and deshielding effect can also be offered by the circulation of sigma electrons. See, in a carbon-hydrogen bond, we have a sigma bond only. In an organic molecule where there is a carbon-carbon sigma bond, single bond. The single bond or sigma bond is made out of 2 electrons. So just like the pi electrons, the sigma electrons can also circulate. And when they are placed, when such a molecule is placed over a magnetic field, the circulation of sigma electrons can also produce a secondary magnetic field. See, in the case of alkanes, the secondary magnetic field produced by the circulation is clearly shown. See, we have cycloalkanes, cyclohexane. In cyclohexane, already we studied about the conformation analysis. Cyclohexane exists in 2 conformations where the protons are in 2 different positions. So we are able to draw conformational structures, chair form and boat form. Okay, in chair form we have 2 conformations, and we can draw the 2 conformations. You yourself can draw. You are all familiar since you have completed BSc chemistry and first MSc chemistry, and you have passed stereochemistry also. So if you give a ring flip, that is, if you rotate one of the carbon-carbon sigma bonds, the axial protons will become equatorial protons, and the equatorial protons will become axial protons. So for the rotation of a carbon-carbon sigma bond, energy is required. The energy is just given by the thermal energy that is received by the molecule. Even if a light amount of energy is given, the carbon-carbon sigma bond will undergo a rotation, and it leads to the ring flipping in cyclohexane molecule. The axial protons become equatorial and the equatorial protons become axial. So the axial and equatorial protons are shown by me. See, here to indicate the anisotropic shielding and deshielding effect that is operating in cyclohexanes, once again I have drawn the geometrical structure, cone-shaped structure. So the first carbon is your alpha position, next one beta, gamma, delta. 4th carbon is your delta carbon. If you come in the reverse direction, alpha, beta dash, gamma dash and delta. So upper side is your gamma dash, beta dash bonds. Gamma, beta bonds. So imagine the cone-shaped structure, and the 2 axes are passing through the center point between beta gamma bonds in cyclohexane. With reference to the beta gamma bond, if you draw 2 axes, then you get a cone-shaped structure. In this cone-shaped structure, you can see the axial proton is lying above the cone-shaped structure, and the equatorial proton is lying within the cone-shaped structure. So we can say the proton, namely equatorial, which is lying in the cone-shaped structure, experiences a deshielding effect. It experiences the maximum field that is applied by the external magnetic field. So its chemical shift value will be lower, whereas the axial proton is not coming in the cone-shaped area. As a result, it is experiencing a higher shielding effect. So, because of the circulation of sigma electrons in compounds containing carbon hydrogen sigma bonds and carbon sigma bonds, the anisotropic shielding and deshielding effect is produced. As a result, the protons of a cyclohexane, namely cycloalkane, they will show two different chemical shift values, one for the axial protons and another one for the equatorial protons. Since the equatorial protons are lying in a higher deshielded area, the chemical shift value is higher for the equatorial protons of cyclohexane molecule. So this is about the anisotropic shielding and deshielding effect shown by the protons in alkanes. The delta values are higher than the axial protons. This is clearly explained. So with this I conclude today's lecture. In the next class we shall continue our discussion on NMR spectroscopy. Thank you.